Alright, silly people, here's the situation. Do you remember when I used to make videos about quantum mechanics? I do too. But today we're going to make a video about calculating like the energy states of the quantum harmonic oscillator. Um, and we're going to be doing that by setting up a function that calculates the Hermit polynomials. And then after we have both of those, we can actually have something which we can use to calculate expectation values of x squared and other things, presumably, at some point. But yeah, um, just getting into it, the first part is the Hermit polynomial function. I'm going to need numpy as per the usual. I'm going to need matplotlib to get some nice stationary state plots, and I'm also going to import the factorial function from math because, I don't know, numpy doesn't have a factorial function, even though it probably should. And so yeah, first bit, define h of n comma x. If n is 0, then it returns 1 according to the problem statement. So I'm just going to do if n equals 0, then it will return 1. If n equals 1, then it's going to return 2 times x. Return 2 times x. Otherwise, we have to use this recursion formula. And I am straight up just going to use recursion for this, even though it's not the fastest way that you could write this code. I just think it's fast enough for our purposes and easy to read. But if you wanted like a faster version, so you can get like order n equals 100, you'd have to do something else. But for this, we're going to return this equation here, but I'm going to massage it so that we have h sub n of x on the left-hand side, and so this will have to be n minus 1, this n will have to be n minus 1, and this n minus 1 will become n minus 2, right? So we got 2 times x times h, n minus 1 comma x minus 2 times n minus 1 times h of n minus 2 comma x, right? Yeah, okay. So that's cool. Then we can define a function which calculates psi of n comma x, which uses the Hermit polynomial thing. So that's going to be e to the minus x squared over 2. So numpy in the return line, numpy exp minus x squared divided by 2. And then it's times the Hermit polynomial times h of n x, and it's divided by a square root. So numpy square root of 2 to the n times n factorial times the square root of pi. So 2n times factorial times numpy square root of numpy dot pi. Great. Then we can get into plotting the first 4 wave functions on the interval of minus 4 to 4, which should be pretty straightforward. We'll just create a input list xls as a numpy linspace from minus 4 to 4 with 1,000 steps, and then create a bunch of plt.plot lines where we're going to plot xls versus psi of 0 for the first one, xls with the label. I'm actually going to use LaTeX for this, slash psi sub 0. Nice. And then I'm going to copy and paste this plot line down. a couple of times to get the other wave functions. So 3, 2, 1 here, 1, 2, 3 here should make that nice, and then at the end we'll have to specify to show a legend, and then that should work. And yeah, look at those beautiful wave functions. How lovely are those? The next bit is to make a separate plot of the wave function for n equals 30 from x equals minus 10 to x equals 10. And this is really going to showcase how fast the recursion is as compared to like any other sort of method you could use. So I'm just going to copy all this stuff from this cell down, stick it down here, and then do pretty much the same thing. Create an input list using a linspace, but this time it's minus 10 to 10 with 1,000 points. And then you plot XOS versus psi of 30 XLS. And I don't really need a label for this one. You can just run it. And it does take some seconds to do that recursion, but it gets there in, this took what, 10.281 seconds. Yeah, if you're going for higher orders of n, you're going to need a different method to do this, but I think that is good enough for us. Last part is to calculate the quantum uncertainty in the position of a particle using this little formula here. And so, and it's a Gaussian quadrature sort of integral. Fun. So I'm going to take this bit of the code again, and I'm going to start setting up some Gaussian quadrature stuff. The thing to realize, though, is that when you have integrals that are on the order of like going to minus infinity to infinity, it's really useful to make a substitution of variables if you wanted to calculate it numerically. So for this, you want to replace x with just the tangent of a thing called z, and then your integral becomes the integral, and I'm going to say this in LaTeX. Your integral of f of x dx becomes the integral of the tangent of z. It's actually f of tangent of z divided by cosine of z squared. And I got that straight out of the book. You can use the same thing. There's a different solution for it, obviously. There's always going to be different solutions. But that was the one that worked for me. And then if it was, yeah, this is for integrals that have the bounds of minus infinity to infinity. Right. And then whenever you use this substitution, the bounds become minus pi over 2 to positive pi over 2. Right? It's kind of intuitive the way that it's derived, and it's ends up being really nice. But yeah, so we're going to define our integrand as per the usual, f of n and z this time, returning it's x squared times the psi of n of x all squared. So it's going to return, first of all, the tangent of z squared, and I should really put that squared inside of these parentheses, but then multiplied by the numpy absolute of psi of n comma x n comma z even. Not even that. N comma numpy tangent of z is what it should be. But then inside the parentheses where the absolute value is going to hang out, you're going to square it. And then you divide by, again, the cosine of z squared. And then you do Gaussian quadrature with n equals 100 points, a equals minus numpy dot pi over 2, b is positive pi over 2, and then Gaussian quadrature happens. So I'm just going to go up here and grab this old slice of Gaussian quadrature code that we've used in multiple videos at this point. So if you're not used to that, maybe go back and watch like the first one of those. But then yeah, we need to modify this function call line though, so that we do 5 comma xp indexed k, because we're doing the n equals 5 wave function for this. And at the end, we can print out the square root of the result of the integral, which is what we are going to be checking against according to the problem statement up here. Should be around 2.3 if we did everything correctly. So let's give it a run. Bada boom, I did it in like a second. So I think everything is okie dokie there. All right.